So very briefly, this paper found that we can use a ubiquitous, extremely abundant fungus called Metarhizium to protect plants from mercury poisoning. The fungus acts as a shield. It grows down from the seed, covering the roots. It absorbs and detoxifies the mercury, so none of the mercury gets into the plant. We also found we extended that. We took the fungus, put it into seawater, fresh water. It could take up any heavy metal contamination, make that water safe to drink. Well, we're dealing with a world with increasing levels of mercury. That's been recognized by the World Health Organization that lists mercury as one of the 10 chemicals with most environmental impact. There are places now in the world where you can't really grow plants, produce substantial crops because of mercury contamination, and that's likely to get worse. So how do we deal with that issue? The way you normally deal with that is to actually remove all the topsoil. Very expensive, difficult to do. But we now have this trick. Metarhizium is easily grown. You can mass produce the fungus. You would simply dip seeds into the fungus, plant them, and they would grow, produce abundant crops on this contaminated soil, just as they would on normal soil. So it's a very cheap, very easy fix to mercury contaminated soils, which could be used anywhere in the world. Metarhizium is already used quite extensively in developing countries. The genesis of this work goes back 20 years. I had a graduate student called Gong Hu, who just by chance, serendipitously, he wasn't looking for it, found that Metarhizium grows on plant roots. For 100 years or more, it's been studied as an insect pathogen. And there's been lots of reports, though, which we found interesting, was that you find Metarhizium growing in soils with very high levels of heavy metals. So we simply put 2 and 2 together. We looked at the fungus. We got fungus which can grow well in mercury. So we wondered, well, is that going to protect corn? Corn, grow it in mercury-contaminated soils, is really badly stunted. So we put the normal, natural, wild-type fungus on the seeds, let the fungus grow down the roots, and it provided a lot of protection. So we thought, can we improve on that? So we took the genes which produce the enzymes which detoxify mercury, and we put extra copies of those genes into the fungus. And we found that by doing that, it produces extra quantities of the enzymes, and that amplified the protective effect of the fungus. So now, we can use that engineered fungus, we can put that on the seeds of the corn, and we can put that corn in heavily contaminated soils, and the corn looks exactly the same, produces exactly the same yield as corn grown on normal soils. So it's perfectly protective. And there's no mercury in the corn. So the corn is edible too. So we've done these studies in the lab. Now we need to do a series of increasingly large field trials in China, in heavily contaminated fields in China, and see if we can benefit corn, see if we can benefit other plants too. So there's different Metarhizium strains. Some are adapted to grasses like corn, some are adapted to shrubs, some are adapted to trees. How far can this protection extend with these different Metarhiziums? We might be able to produce Metarhizium plant combinations, optimized combinations. We're also investigating alternatives to genetic engineering. Genetic engineering means regulatory hurdles to overcome before you actually put things out in the field. Can we, say, do chemical mutagenesis to amplify production of these enzymes in fungi? What other tricks can we use besides doing genetic engineering? That should be possible. But after all, we are using the fungus's own genes. We're simply putting extra copies of the fungus's own genes into the fungus. We're also, though, interested in those genes in themselves. As I said, we can put those genes into other fungi, and those fungi now can protect themselves against mercury. So how can we use this as these genes as a kind of cassette, a toolkit, which we can put into other systems? Could we put the genes directly into plants so the plant now can protect itself? After all, the fungus is protecting the plant with these genes. Could the plant now protect itself if it had the genes? Presumably, yes, it could. it was, if you like, it was a long shot. We put the fungus into salt water, we put the fungus into fresh water, which was heavily contaminated with mercury. With a couple of days, all the contamination was gone. How do we exploit that? Could you imagine, say, for example, putting the fungus in columns and putting contaminated water through the fungal columns to clear it up? Could the fungus be used in wetlands, which in several parts of the world now are heavily contaminated with heavy metals? Could the fungus be used as a to decontaminate, to purify those wetlands, to improve the ecology of those wetlands? So we're interested in applying it in different ways. How far can we extend this new resource? How useful can we make it? This fungus is present everywhere. You could go outside here, you could go into your garden, you could go into Africa or India or anywhere else, take a gram of soil, you will find the fungus. It is one of the most abundant eukaryotic organisms out there. And it also has a track record of use against insects going back 70 years. So a track record of safe usage. Lots of high quality studies showing that this fungus is safe to everything except the insects it targets. So we're probably looking at a previously unknown natural part of the Mercury cycle. So, you know, why isn't it? Well, it almost certainly is. We just didn't know it before. So if we didn't have natural wild-type metallizium, it might well be there's much more abundant levels of heavy metals in the environment. So we're looking at a world now which is already protected probably by these fungi. After all, why does the fungi have these genes in the first place if it doesn't need to use them? It's clearly in its history come across mercury contamination. So we would be using metallizium, which is shown to provide protection against mercury. We'd be applying that on the seeds. So a heavy dose of the fungus on the seed. So as the seed germinates and grows, the fungus, this metallizium, if you like, will be the primary colonizer. In the field, metallizium is competing against lots of bacteria, lots of other fungi, and so, you know, it's a small component of the total population. Here we start off with a heavy dose of metallizium. That gives it a big advantage in colonizing the root. What interests people? The big story in science is always evolution. And here we're looking at the evolution of a symbiosis, how two organisms interact and help each other out. The plant provides a habitat. The fungus is extremely interested in protecting its habitat. So we're looking at the evolution of a relationship. Anything you tie into evolution is a big story. We're also tying it in, of course, to pollution and to global warming and the impacts. Burning of fossil fuels with mining, mercury has been accumulating in the atmosphere. And what came as a bit of a surprise to us was there's huge amounts of organic mercury in the tundra, in the permafrost. And as global warming is melting that, then the mercury is being released. So vast quantities of mercury are being released just by the melting of the tundra. So global warming, human impacts on the environment, and a good story of two friends, the plant and the fungus, helping each other out.